To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. Consider the capacitor. The most basic property is the relationship between current I and voltage V, which is a differentiation. The relationship is written with an implicit notion that V is the primary entity or input, and I is the derived entity or output. It is just as equivalent if the relationship is reversed. Let I be the primary or input, then V is the derived or output, then the mathematical operation is the inverse of the previous, that is, it is an integration. Hence, differentiation or integration are two sides of the same coin. If one side is considered, it is necessary to view the other side. Let's start with differentiation. Let input voltage V be a sum of two parts, a DC component, constant versus time, and an AC component, varying versus time. Then, the derivative of the DC component yields 0, leaving only the AC component. This is actually the most common use of the capacitor, that is, to block out, or filter out an unwanted DC component. Let's consider a simplest VAC, a pure harmonic of frequency omega. Then the derivative is also a harmonic. However, the output amplitude is not constant, but increasing versus frequency. Effectively, it acts like a device with a frequency preference. It prefers high frequency over low frequency, behaving like a frequency-dependent resistor, or more accurately, impedance. Now, let's consider integration. Let the input current I be the sum of a DC component and AC component also. Then the DC term cumulates versus time. This is the accumulation of charge on the capacitor that we have seen previously. Taking the time average, it becomes the DC term again, plus the time average of the AC current integration. By the very definition, the long-term average of the AC integration is to vanish, leaving only the DC component. Hence, integration is the reverse of differentiation. Differentiation blocks the DC, let through the AC. Integration is to smooth out the cumulative AC component to 0, and keep only the DC. This is the same concept as averaging the measurements of something that fluctuates. We take the mean of the fluctuating quantity to get rid of the variation, or the AC noise, in order to get the mean, which is the true value of the quantity of interest. Consider the AC current be a pure harmonic with frequency omega also. Then the integration is also a harmonic but with an amplitude that is 1 over frequency. This terms means that the higher the frequency, the lower is the output amplitude. Again, this is exactly the reverse of differentiation on the left. Hence, integration also acts like a frequency-dependent impedance. It lets through low frequency, and blocks high frequency. Both of these behaviors are quite fundamental to the capacitor, and they are the reason why the capacitor is so useful. These functions are the building blocks, or the basic tool sets that one can use to construct circuits for controls and signal processings. Consider now the practical implementation of the concepts discussed previously. For differentiation on the left, if the input is V, then the output current needs a transimpedance amplifier to convert it to voltage also, so that both input and output signals are voltage. Likewise for integration. Both types of transimpedance amplifiers can be implemented with the op-amp. This is the basic idea of the circuits in this lab assignment. Consider input voltage V in, coupled to capacitor C1. The current I input to the inverting terminal, node A, is proportional to the derivative of V input. The output voltage, via the feedback resistance, provides the negative feedback current IFB. Applying Kirchhoff's current law at node A leads to the relationship of V out being linearly proportional to the derivative of V input. This is a differentiator or a high-pass filter. A similar approach can be applied to the integration case. The input impedance is a resistor and the feedback impedance is a capacitor, oppositely to the differentiation case. The resulting V-out voltage is an integration of the input V-in, and the circuit is an integrator or a low-pass filter. There are two designs for the differentiation circuit of Part B. Check components you have and think carefully before committing to one, although it is quite trivial to change from one to the other if you have all the necessary components. Essential to design one is the damping capacitance that should be 2.2 nanofarad. It is to dampen the resonance oscillation for abrupt or step output in response to an input slope discontinuity. The capacitance value matches to the LM741 op-amp bandwidth and the design feedback resistance. A more detailed discussion is given in the appendix. If you don't have the components for design 1, consider design 2, in which a dampening resistance value of 47 or 50 ohm is needed. Many without sufficient capacitors have chosen this design in the past. Both are adequate for the experiments of Part B. At this stage, the design process is a bit more complicated. It is virtually impossible that everyone in the class has the exact components of the nominal design. In reality, flexibility in a design is actually a virtue. For this lab assignment, however, because there will be a series of measurements to be performed for which the input and output signals are to be within certain parameters, altered circuits should be checked to ensure that the circuit will perform within the boundary. This app is a tool for this purpose, in order for one to check the tolerance of the change of each component. The following is not a full instruction how to use the app, it is only to introduce the app, to explain why component considerations should be done before building the circuit. Of course, replacement of components of an already built circuit is also straightforward, and it is not absolutely essential to do this, if one expects to have replacement components later. More details how to use the app are given in the appendix. If you choose Design 2, it will be shown after this. This is an example of a differentiator, high-pass filter circuit, and an integrator, low-pass filter circuit. They don't have exactly the layout as in the wiring app software. Here, the plus 12 volt and minus 12 volt supplies are on two separated outer rails, and the ground are on the two inner rails. For use with the DG-Lent AD2, the wavegain signal 1 and signal 2 can be used as the inputs to the differentiator or integrator, respectively, or vice versa. Both scope channels are used to monitor the input and output of each circuit. Given only two channels, only one circuit can be measured at a time. The 6-pin connectors have wires connected to both input and output of the circuits, and the scope input cables can be mechanically multiplexed to appropriate pins as needed. This is a detailed illustration of the connection of two oscilloscope channels to the input and output of the differentiator high-pass filter circuit. For design 2 of the differentiator high-pass filter circuit, the key difference from design 1 is the damping resistance. In this photograph, two 100 ohm resistors are put in parallel for 50 ohm resistance. A single 47 ohm would work equivalently. The nominal values of the components for design 2 are shown in the table at the top right. Since this design is not in the circuit simulation app, if you wish to test out the values of components you have, use the model in the appendix to fine-tune the transfer function. Its experimental Bode plot will be shown later for reference and comparison. Do not be concerned if you are not familiar with Laplace transformed circuit. The only thing matters is the frequency response that is appropriate for the required experiments, which are quite flexible. Much of the work in tasks B2 to B5 are similar to that of Lab 4 Part A. Again, the exact experimental parameters are not critical, and it is more important that you understand the rationale behind each task and do the work, rather than just blindly follow instructions. The following are a series of videos that are examples of tasks B2 to B5. Each video is self-contained for the uninitiated, hence, some information at the beginning are repetitive. It is not necessary to follow exactly like what done in the examples. The essence is to understand the objectives of the experiments, namely to test the performance of the differentiator high-pass filter circuit, and perform the tasks to accomplish the objectives. The circuit labeled differentiation in the photograph is tested in the follow. The two scope channels are connected to display the input and output. The derivative of a triangle waveform signal is a square wave. Observe the output amplitude as a function of frequency. It has the high-pass filter behavior as it allows high frequency passing through while attenuating low-frequency signals. On the fast time scale, or high time resolution, square edge shows roll-off, limited by the op-amp bandwidth. The damping capacitance introduces near-critical damping, and reduces the underdamped oscillation. Higher capacitance would make it overdamped. One can pull out the damping feedback capacitance to see the oscillation. The waveform is no longer square at higher frequency. Eventually, it approaches sinusoidal, as only the fundamental harmonics of the Fourier spectrum remains. Here, we encounter the concept of frequency response again, which was done for the op-amp voltage amplifier in Lab 4. The behavior of the gain versus frequency appears to be opposite in this case. The circuit favors high frequency over low frequency. This behavior is also known as high-pass filter, a device that selectively let the high-frequency signal to get through with higher amplitude than the low-frequency signal. The outcome of this step should include Bode plots. Please follow the instructional video if necessary. The first sanity check is to look for the 90-degree phase shift expected for the derivative of a sinusoidal. Beware of dg-lent AD2 potential errors in some measurement functions. This pitfall has been discussed in previous lab. In order to obtain accurate measurements, it is necessary to collect the waveforms over several periods as illustrated. It is recommended to save the data files in CSV format, then use the harmonic signal processing app that was used in Lab 4 to obtain the amplitude gain and phase. It is important to be aware of what to be expected, and use sanity check to ensure valid measurements. Potential and actual errors will be discussed next. This graphics illustrates a typical pitfall with dg-lent waveforms software. The graph shows output of waveforms software Bode plot function. The plot is invalid. This problem happened to some students' circuits, and less severe for others' circuits. Yet, based on the raw collected data of the scope, analysis with our own signal processing app produced valid Bode plots as shown next. The left-hand side shows typical amplitude and phase Bode plots. The experimental data points obtained from the harmonic signal processing app show smooth behavior, unlike the output of dg-lent waveforms software shown above, using exactly the same scope setup. The dashed theoretical curves from the simulation app agree well with the experimental results for the frequency range below the LM741 bandwidth. The calculation was done with the nominal, not measured values of the various R and C components. If these values were allowed to vary, an even better fit would be obtained. It is recommended to use the circuit simulation app as shown on the right-hand side with the circuit actual component values, to know what to be expected during the experiment. It can help sanity check, avoid erroneous setup or spurious effects, before collecting a large volume of data only to be found invalid later. For the circuit of design 2, as shown on the left, a more realistic op-amp transfer function was used, producing the agreement between the experimental Bode plots on the right-hand side and the theory. The data are marked by the points and lines connecting the points. The theoretical calculation is represented by the dashed curves. Reasonable agreement was obtained as expected. This part is quite interesting. What is the derivative of a discontinuous step, mathematically known as the Heaviside step function? It is an impulse function of infinite magnitude, also known as Dirac delta function. However, a real physical system can only have a finite response, and the output impulse has a finite time duration that is inversely proportional with the system bandwidth. This figure is a very important parameter in the days of analog PID controllers about 2 decades ago. Please follow the instructional video if necessary. Finally, we are at the end of part B. It is for both learning and amusement to see how the circuit performs differentiation on various common waveforms. There will be custom waveforms to test your circuit. Please follow the instructional video if necessary. Please include all your experimental data, analysis, and discussion in your report.